I purposely write my E's with a capital E. And epsilon is a Greek symbol, not one of those Greek symbols. Looks like a little curly E.
Okay, it's equal to what?
0.1. So we want to compare 1 with n. This is f of n minus epsilon. Alright, so for part B, would you use the master theorem to work it out? That's a chip of uncle recursion. So master theorem no good there. Part C. Actually, it looks like the violent cut. It looks like a mixture. Actually, there is a special case that we did not go into where we could actually simplify that expression. So let's just work it out. So if T of n is equal to T of n minus 1 upon 2 plus 1, there is a proof that this expression has the same order of growth as T of n upon 2 plus 1. We won't go into the proof right now. We'll just simplify it. We can simplify to as long as you're subtracting from a constant and dividing, you can simplify by dropping one constant. The proof is there somewhere, but we don't have time to look at it now. And then we can solve that with master theorem, right? So we can, f of n is 1, E would be equal to there's no A?
No. 1.
If A is 1. Log to the base 2 of 1, which is equal to 0. Log to the base of any number of 1 is 0. So, with that A is 0, what would be the exponent of f of n? No, f of n is 1. The exponent would be 0. In the same way, or let me just write out using the other way. I mean, you can decide to use that if you want. I'm just going to use this strategy. I think it's easier to explain. If you want to fall back to that. So we see that of n to the e. Because if that is 0, e is 0, that implies that n to the e equal n to the 0 equal 1. Right? So both f of n and n to the e grow at the same rate. So therefore, what case applies? So therefore, T of n is equal to
of n
times G of n. F of n LGN is equal, f of n is 1, so that's theta should have closed the bracket outside there. Right. Theta of LGN.